Bonjour à tous et à toutes. Mon nom est Franco Saliola. Je suis le nouveau directeur adjoint scientifique du Centre de recherche mathématiques, le CRM. So I am Franco Saliola. I am the new scientific deputy director of the CRM. On behalf of the CRM, I'd like to, first of all, apologize for the technical issues and then welcome you to the Andre Eisenstadt CRM lecture series. Andre Eisenstadt was a successful businessman who held a doctorate in theoretical physics from the University of Zurich and who was a mathematics enthusiast all his life. In 1991, he received the high distinction of Grand Officer of the Ordre National du Québec. And for more than 20 years, Andre Eisenstadt supported mathematics research, including its dissemination to the general public through the creation of these Eisenstadt Chair program. The Eisenstadt Chairs were created in the early 1970s, just actually a few years after the CRM was founded itself, and they quickly became an important part of the CRM thematic semester program. The Eisenstadt Chair enables each thematic program to welcome world-famous mathematicians to give a series of 3 lectures, and in accordance with the wishes of Andre Eisenstadt himself, the first of these lectures should be aimed at a wide mathematical audience. To introduce the Eisenstadt Chair recipient this time and today's lecture, I present Jean-Philippe Lézard, who is also one of the co-organizers of the thematic program.
Merci beaucoup. Tout d'abord, bienvenue tout le monde. Hein. C'est la première activité. En fait, on vient de terminer une activité au CRM qui est un tutoriel. Et là, c'est notre première grande activité de la session. Donc, on va avoir une session thématique du mois de septembre jusqu'à la fin du mois de novembre. Et l'exposé de Javier, c'est notre premier grand événement. So thank you very much for everyone for being here. We just finished a tutorial in this thematic program that just began. This is our program entitled Computational Dynamics, Analysis, Topology and Data. So today for our first chair lecture. I will have another one from Javier next Wednesday and on the 25th as well, and Rachel Kuske, who's at the back. She will be our other chair, and her lecture will be slightly later in the semester. We'll have 3 workshops and 2 tutorials, and one of them just finished today. Okay, so without further ado, I would like to warmly welcome Javier Gòmez Serrano. We're very happy you could make it. Javier got his PhD in 2013 from University of Madrid in Spain. And then he moved to Princeton for about 7 years, where he worked a lot with Charles Pfefferman and started to spread this idea that, combining the computer with very smart analysis and nowadays machine learning can actually lead to great results. That we'll in fact witness next Wednesday, because he'll talk about a very exciting result involving blowups in fluids. That's, as far as I can tell, one of the greatest achievement in the field nowadays. And today he'll be talking about a more general audience talk. But before that, let me say that he's very well accomplished. He was in Princeton for 7 years. Then he moved to Brown in 2022. And in between that, he had 2 years where he was oscillating between Barcelona and Brown. And now he's an associate professor at Brown. He's won several awards involving, and then for this I need the list, involving the Antonio Ambrosetti Medal in 2023. He won the Antonio Valle Prize for the best Spanish applied mathematician under 33, very interesting age, in 2018. And then he won the Vincent Cassel Prize for the best Spanish mathematician, not applied mathematician, but mathematician, under 32. Yeah, and then he won a couple of other prizes. Let me not overburden you with his achievements. So please welcome Javier.
Okay, thank you. Yeah, thanks a lot for everyone to coming. Premier de tout, mon français c'est pas trop bon pour donner cet exposé. Alors je la ferai en anglais. So I'm sorry, I'll switch to English right now. So yeah, thanks a lot to Jean-Philippe and all the other organizers, Jambao, Maxime, Jay. Thank you everyone from the audience for being here. So today I'm going to give a lecture titled Mathematics and Machines, Navigating New Frontiers, which in the beginning, when when I was tasked to give a series of lectures, and the first one being for the general public, I really took it as the general public. So in other words, I took it as, how can I explain my grandmother how the hell I'm making a life out of this, and what do I do every day that that I go to work? Okay, so this is going to be extremely basic, absolutely no equations whatsoever in the entire talk. Lots of pictures. Feel free to stop me anytime. If you came here looking for a more hardcore technical talk, wait until Wednesday, as Jean-Philippe announced. Yeah, my plan is to sort of recap kind of my own journey through the field, through the last 10 years or so, and even going back to 30, 40 years, and explain how the community has evolved, how the perception of the community has evolved, and also what lies after. Okay, so think of this as kind of my own view, my own personal touch, my own personal opinion. That's kind of a disclaimer about this whole field of computer-assisted proofs and mathematics, or the interaction in general between computers whatsoever and mathematics. Okay, I'm going to talk a little bit about computers and computer-assisted proofs and mathematics. Okay, so let me start by looking at how awake the audience is, by posing this a little mathematical problem. Just tell me what is this function f evaluated at this point, 77,000 ... 33,000 ... So this is credited to Gump from 1988, and you'll see in a minute why I chose this function and those numbers. No? Okay, good guess. No. It's not one either. So let me, I understand this is difficult, no? If you try to do 77,000 to the fourth, 33,000 to the fourth power, it's a big number. So let me change a little bit the question, and let me ask you, what would a computer say if I were to ask the same question to a computer? Okay, this is an easier question. Any guess? Overflow maybe? Zero maybe? No, it's actually a good guess. So let's see. The short answer is depends. Depends on the computer. Okay, so if I were to write a program, let's say in C++, it doesn't really matter, but just for illustration purposes, and I run the computation of that function with single precision, then, okay, it doesn't say overflow, but it says some big number, okay, 10 to the 12, 4 times 10 to the 12. If I were to run it with more precision, then it tells me 1.17 ... If I were to run it with even more precision, then it keeps telling me 1.17 ... So typically, what would many people do? Well, if I have done my calculations like this, they stabilize after I increase the precision. We're done. Let's call it a day. Okay, this is why rockets explode sometimes. So let's do another experiment, and let's run the same piece of code in other language with a different precision. So now suppose that I tell Mathematica, well, tell me what is this? Use 20 digits of precision, and Mathematica says 0. But Mathematica is sort of polite, and in a kind of apologetic way, it says, well, I'm sorry, but I don't really know. There may be issues here. I'm not entirely sure. Watch out, because I'm saying 0, but maybe it's not 0. And then if you ask for more, then it says, whoa, minus 0.082. So this has almost nothing to do with this. I mean, not even the sign is right. They're both like order 1, but if something had to go forward, well, it's meant to go backwards. Okay, so again, rockets explode because of things like this. Okay, so if you remember, the function itself was a rational function, and it's evaluated on integers. So the final result is a rational number. We can compute with integer arithmetic, have infinite precision, and get the right answer. So the right answer is this fraction over here, which turns out to be what we got after we put 50 digits of precision. Of course, here we know how many we have to put in order to get the right answer. That's cheating, because in practice, we will never know when this is correct or this is correct. Okay, so that's a problem. That's a problem, and it kind of builds on the idea of this mistrust about computers. That honestly, it's a mistake, and you see why. So, so the natural question is, after seeing this, is, well, does the computer influence my result concerning hardware issues, precision issues, even the way the code is set up? Because some things that in the mathematical world are equivalent, maybe when you program them and you reverse the order of operations or things like that, is it going to give the same answer? So no, and therefore the answer to this is yes, which is, well, sad. However, can we do something? So can we still use computers to prove a mathematically rigorous theorem? And the nice thing about this is that this is also yes. Okay, so even despite that we have this issue over here, we will be able to overcome it by paying some price, but yet we will get something out of it in the form of a mathematically rigorous theorem. Okay, so as I said, this is sort of my journey when I arrived in the US 10 years ago, and I told people, oh, I work on computer-assisted proofs, and I'm sure other people in the audience probably have experienced this as well. Then immediately 99.9% of everybody that I talked to, they said, oh, the four-color theorem, you're doing things like that. I said, no, absolutely not. I don't use the computer like that. And then the conversation sometimes even went even worse, because people started saying like, oh, but then what you do only works for whenever you have an insane amount of discrete configurations. You have to enumerate them and then study those cases. That was kind of polite. But then sometimes the conversation even got a lot worse. People claimed that this was unreadable, controversial, and that we didn't learn anything out of this kind of proofs and this way of thinking and this sort of methodology. Okay, so this is something that has gotten better. Still, it's not fully resolved, but certainly this is part of, I believe, everybody who has been in this field through their own journey. Okay, so let me clarify and demystify these sort of common wrong beliefs, okay, about what is actually a computer-assisted proof. So I claim that all the claims in the previous slide are false, or they don't necessarily need to be right. In the sense that the fact that this is only useful for discrete problems is definitely not true. So one can still prove results for continuous configurations, space of infinite dimension. That's not a problem, as long as you can have some kind of open conditions and you can bound errors and squeeze into whatever estimates or whatever things you want to prove. As to whether this is unreadable, honestly, now there are papers that are several hundreds of pages, and I don't think that's more unreadable than reading 5,000 lines of well-documented code. And the fact that we don't understand anything, or that we don't really understand the problem, is also not true, because sometimes people think that working on these problems is just simple and easy. You turn on the computer, press a button, wait, and then some magic happens, and you get an answer. And this is obviously not true either. And there is plenty of work to get there. So lots of new algorithms have to be developed. And through those, you also obtain many structural information about the problem. So you really learn a lot about what you're trying to solve by trying to solve it in this way. And on top of that, it has proved repeatedly that it has been, or it can be, highly successful where, let's say, more traditional methods also fail. Okay. So this is my sketch of what I have in my mind when I think about a proof or a computer-assisted proof, which is namely you start with a problem which could be infinite dimensional, definitely infeasible by hand, and then you perform some sort of reduction into a finite set of calculations, into a finite set of conditions that the computer will check. And this is what you code, taking into account all the rigorous errors and so on, and what the computer will say yes, no, or I don't know. And if yes, then then you have a theorem. Okay, so this is sort of the pipeline of a computer-assisted proof in my head. Okay, just to as I said, this is about the journey. Let's take a little jump and get into the present. These are all the abstracts from the talks from next week, which I would make a small advertisement, and I encourage people to come to the workshop from next week. And okay, the font is small to fit them all, but what you can see here are definitely keywords that don't really look like old technology, like old problems that nobody really cares about. So you see Navier-Stokes, KAM, PDE, DDE, non-self-adjoint operators, large-scale computations, and so on. So definitely people are really trying to achieve big things and big goals using this kind of technique. So they are really tackling big problems and big questions nowadays. This is really the present. I mean, it's the next week present. Then some people may argue, well, but this is maybe just in dynamics, no? What about other fields? Are people from other fields really taking notice of this? Is this a niche sort of technique that only applies to your problem and their close cousins or whatever? And this is also not true. So there are pretty recent theorems in fields such as spectral theory or mathematical physics or even group theory, some of them done by people from Montreal, where they really solve very important and old questions from, okay, 70, more than 100. This is also a very old question as well, using very clever methods that a priori may not have anything to do with this sort of field, but that they were designed for doing that. And this sort of interplay between the computer-assisted part and whatever the group theory or whatever problem they are doing is it's quite impressive. So certainly these techniques are happening now, and people are taking advantage of them to solve old questions that nobody seemed to get a hold of them until now. Okay, so this is not just happening like right out of the blue. Okay, so this is a journey. This is a process that has taken many years, and you have to start somewhere. And then throughout the last years, especially, you can see like the emergence and the speed of how things have gotten up until now in terms of productivity and the amount of material and methods, and also related to the hardware and software improvement in computers. So in the very early days, let's say 80s, 90s, 20s, results and people were driven by problems. Okay, so because I mean there were software and hardware limitations, and the techniques weren't maybe as popular. So problems coming from mathematical physics or dynamical systems that were solved in the early days. But now things have gotten much more popular, and really the modern technologies rely on all of these people, including many of them who are in the audience, that have allowed modern computer-assisted proofs to be built upon what they themselves built. Okay, so At least personally, I am very, very grateful for them to have created both theory, but also methods and even libraries that that people can use, and that nowadays I personally benefit from them, but also other people, and this pushes really the science a lot further. So now let me give a very small taste about my own work. So I have been in this business for about 10 years or so, and I will mention very briefly 3.5, let's say, results that I like, that they are very different from each other, and that somehow have slightly different flavors from each other, and that I have managed to prove using a computer-assisted method or a computer-assisted attack. So the first one was done with Joel Dane, who was my former PhD student in the University of Uppsala. And we proved that for a certain PDE, this is really, the PDE itself is not relevant. We were able to construct, by using computer-assisted methods, a non-smooth traveling wave solution with very highly accurate quantitative estimates of the profile itself. And this is something that people had tried using abstract bifurcation theory and had failed in the past. Another thing that, so this is one instance of one problem, in the sense that we are constructing one object that satisfies a certain condition. Then, in fact, it is before, we constructed a family of objects that satisfied another condition. In this case, these were the first example of smooth initial data that solve something called the SQG equation, which is a model for the incompressible 3D Euler equation for which there is global existence. So this was an open problem for many, many years, whether initial data may develop finite time singularities, or on the contrary, they will lead to global in time solutions. And we managed to give an example of a family that had this global existence behavior. So now we have passed from something which is concrete to a family of things that solve or that have a certain property. And these two things are, let's say, PDE problems or PDE solutions. I also managed, together with Gerardo Riols, who was an undergraduate at the time, to show some nice result in spectral geometry, so in the geometry of the Laplacian on the plane, showing that if you have two triangles, they are not determined by a set of three eigenvalues. So if you take three eigenvalues, then the triangle is not determined. In other words, we constructed, in this case, a family again of triangles that were isospectral at the level of three eigenvalues, but not isometric. Okay. And I would also like to mention some ongoing work with Alberto Enciso, in which we prove that, again, this is, okay, so the third one is again a family, and this is now a big family, and even something very, very big in the class of domains that essentially says that ellipses are robustly dynamically spectrally rigid. Okay, I won't enter into the precise definition of what this means, but just to clear ideas, it's some form of a spectral rigidity for a certain class of domains, in this case of the plane. Okay, so so far, this is what I think about the past and about the present. And towards the future, I think we are living really great times for computer-assisted proofs. And it is a great time to really dive in, especially if you're a student. I think this now is a great moment where you have lots of tools. It's not overcrowded. There are plenty of interesting problems. Hardware is very cheap. You can now, in the old days, computing things was very expensive, and getting the right equipment was very expensive. Now hardware is very cheap, and you can get computing resources easily. And this really has a lot of potential than just sticking to traditional methods. So the more you know, the better it will be. So I really want to encourage people and want to, especially young people, to sort of keep this in mind and think about getting in the field. And there is certainly plenty of room and lots of available, doable, interesting problems at this point in time. Okay. And if I were to bet, I think these kind of methods put together with other maybe traditional methods are going to become influential in the next 5 or 10 years, even more so. So let me talk now a bit about machine learning and math. So machine learning now is really a buzzword. Everybody doing machine learning. And well, I've also started doing machine learning myself. Okay, I have to admit that. So let me give you sort of my take on this interaction. And people really have very strong opinions. I mean, it's surprising and they're so different depending on the person. So people really are very opinionated about machine learning and in the context of mathematics. So let me start by talking about machine learning in general, not machine learning in math. So this is, you've probably heard about this. This is AlphaFold and the press release by Nature 2022 when they won the $3 million breakthrough prize. AlphaFold, to summarize it, is the output of a group of people working for Google DeepMind that had absolutely no prior background in biology. They knew nothing about it. Some had some background in physics, but they knew a lot of machine learning. And by doing that, they were able to beat all the biologists in their own turf. And they managed to develop the best software when it comes to predictions about the structure of proteins or protein folding in general, which is one of the biggest problems in biology. Okay, so the moral of the story is some random dudes that are very smart outsmart everybody else in the room by taking a completely orthogonal approach and doing things their own way using machine learning. Okay, that's fine. What about mathematics? Well, the thing is they also started working and doing mathematics. So this is a Nature paper, December 2021. Let me read a little bit the abstract. So they say, the practice of mathematics involves discovering patterns and using these to formulate and prove conjectures, resulting in theorems. Here, we provide examples of new fundamental results in pure mathematics that have been discovered with the assistance of machine learning, demonstrating a method by which machine learning can aid mathematicians in discovering new conjectures and theorems. So essentially, the message now is that using machine learning, you can get to see far beyond what you can see when you didn't use it. And using these things, they were able to first conjecture and then prove some results in knot theory. Okay, so the claim is that AI or machine learning can be a useful companion in mathematics for discovering new things. What new things? We'll see. This is sort of a similar press release. Quanta, machine learning becomes a mathematical collaborator. 2 recent collaborations between mathematicians and DeepMind demonstrate the potential of machine learning to help researchers generate new mathematical conjectures. Okay, same message. You combine mathematical insights with machine learning, you get a new conjecture, you get a new theorem. Okay, that's sort of the plan for this, at least at this stage. Another one, Nature. For the first time, machine learning has spotted mathematical connections that humans have missed. Same story, same message. Okay, so now, if you talk to people about this, there are really 2 opinions. The end of the world is near, and AI is going to take over, and people are very worried about this. And especially if you talk to some mathematicians, some people think they're going to lose their jobs immediately. Now, is AI going to be so powerful that we're not going to be needed anymore. AI is going to be doing the whole thing, creating the conjectures, proving them, and discovering everything. Well, some things are worrisome concerning that stance. Again, Nature, January 2024. So IMO stands for the International Mathematical Olympiad. This is the most prestigious contest at the high school level worldwide. And the title says Solving Olympiad Geometry Without Human Demonstrations. You can imagine what the paper is about. They say proving mathematical theorems at the Olympiad level represents a notable milestone in human-level automated reasoning. We propose alpha geometry, a theorem prover for Euclidean plane geometry that solves a lot of problems. Okay, so AI now can solve a good amount of geometry problems that are posed at the International Mathematical Olympiad. Okay, January 2024. July 2024, now strike the geometry, all problems. So AI now can solve enough, which is about 2/3, to achieve a silver medal at the International Olympiad if they were a human contestant. Okay, I mean, presumably the headline for 2025, you can guess what it's going to be. Okay, so now is this really going to grow enough that it's not going to be just IMO problems, but math? That's one take on this. Then I get the other take. Like, all of this is just BS. This is all hype. I don't believe any of that. And this is kind of a new mechanical Turk. And I have to admit, I thought like this, maybe about 3 or 4 years ago. And then I got quickly convinced that this was not the case. Okay, so, and I'll explain also my journey through this conversion from thinking like this, like AI is useless, just a lot of marketing, with my current opinion, which is definitely much more positive. So, so just to give an explanation of what the mechanical Turk is, if you don't know what this is. So this is, well, the AI of the 1770s. So this was a mechanically engineered chess player that was very, very good. And humans could play with the machine. There are lots of like bolts and wheels and lots of mechanical stuff inside the box. This was at the level of a master or perhaps even a grandmaster. It was beating most of the human players of the late 1800s. Okay, now the issue with that is that, well, the AI of the 1770s turned out to be not very artificial. And in fact, there was a grandmaster inside the box, and they were able to fool lots of people for about 80 years or so. But then at the end, it was discovered that the way the whole system was engineered and the whole way the system worked was through not that artificial intelligence anymore. Okay, so you end up meeting like people with these two kind of opinions, and this is mine. Okay, so I don't think this is a hoax. I don't think this is useless in the context of mathematics. I think it will stay. So it has come to stay, but it will coexist. And I think it will need traditional mathematics. It will need mathematical insight. And I don't think it will be able to solve things on their own. The end of the world is not near, and we'll keep our jobs. We don't really understand it well enough, and we don't really understand why certain things are done one way, and this is an issue. I think it will be resolved in the future, but as of today, we don't really know why things work, why the output is the way it is. However, whenever we really understand it, there is really a lot of power, and it will definitely help, and it will certainly shape many fields. So by taming artificial intelligence, by taming machine learning, I think lots of discoveries can and will be done in the near future. Again, let me stress my point. This is a commercial from the mid-1990s, back when I was a kid. So even if you have a lot of power, there needs to be a mathematician behind the wheels. Like, just things on their own, I don't think they will create or destroy everything. And yet, mathematical insight, mathematical formulation, techniques, theory is going to be really needed to cooperate with AI in order to advance. Again, that's kind of my personal opinion. Now, let me talk a little bit about recent success stories involving AI and mathematics. Okay, so this is called murmurations, and you can guess why the name from the picture, because this is very similar to the murmurations from birds. This is why they coined the name for this phenomenon after seeing the picture. So I'm absolutely not an expert in L functions and elliptic curves. What they're plotting here is the following. So you take many elliptic curves, then from those elliptic curves, you can compute something for every prime, some number that is related to L functions that is called AP, depends on P. And then you average over all these curves that satisfy that they have a conductor between 7,500 and 10,000. And what you get, depending on whether the curve has rank 0 or rank 1, which is most of the elliptic curves, is this nice structure that it hadn't been observed before. So people using machine learning methods, they were able to figure out very well the APs. And then from the APs, they were able to attack these averages and have this sort of nice plot. As far as I can tell, before the discovery, none of the number theories knew anything about it. Now there are proofs, but this was really a striking phenomenon in the number theory community. And it was done due to exploration and discovery involving the capacity, the calculation capacity given by machine learning. Okay, in some other unrelated fields, for example, in physics, all of these people are computational physicists or somewhat in between mathematicians and computational physicists, have been using machine learning to compute Calabi-Yau manifolds. Okay, so by now, this is standard in computational physics, and it's getting into mathematics. So the computation of Calabi-Yau manifolds, as far as I know, is very difficult because you have to do integrals on very high dimensions, and you get the precision is terrible. But by using machine learning techniques, they have been able to really lower down the errors and really compute these manifolds with a very high degree of precision. So this is also another example that it's kind of unrelated, but another area of mathematics where really it's starting to be picked up, this influence of AI in the whole field of mathematics. And finally, I want to talk about PDE. This is a Quanta article on my own work that says, so the headline is Deep Learning Poised to Blow Up Famed Fluid Equations. For centuries, mathematicians have tried to prove that Euler's fluid equations can produce nonsensical answers. A new approach to machine learning has researchers betting that blow up is near. So this was written when we released a paper, and we used machine learning to compute candidates for which the incompressible 3D Euler equations could blow up. Okay, as I said, machine learning is not going to be everything, This is another Quanta article on kind of similar results using non-AI techniques, but a computer-assisted proof. So the headline again is computer proof blows up centuries-old fluid equations. And in 2023, Chen and Hao released 2 papers, each about 150 pages, with a proof of singularity formation for incompressible 3D Euler with boundary. And the proof doesn't use AI, but is computer assisted. So you could see really the influence of computers in general in modern mathematics or in modern PDE. Okay, let me now give a very brief explanation about the technical part. Again, it's going to be very, very light. So I will try to make everything as easy as I can. In a nutshell, what a neural network is let's pretend for now that it's a black box that takes input variables and outputs output variables. And then the whole point, the whole goal of this neural network is to find the formula for whatever we're trying to find. Okay, so I cannot be more abstract than that. You have input, output, and you want to figure out a formula that solves something or describes something. So in the beginning, in the early years, when people talk, for example, about supervised learning, then the input were essentially images of dogs and cats, and the output was a function that told you 0 if the image was a dog, or 1 if it was a cat, or digits, or plates, or things like that. So this was all supervised because the way to find this function was based on a set of examples that you had cataloged by hand. Then somehow the network could figure out a way to sort of parameterize this function of being a dog. Okay, this is in the early years. Now let's go to maybe more modern. So for example, in the paper about the knot theory, this is still supervised, but now, okay, we're not trying to catalog dogs and cats. And the output is going to be some collection of knot invariants. And the neural network is trained on some huge database of knots. And based on that, it tries to find new relations. It tries to find new relations between properties of the knots. And this is the way they found, I mean, I'm overly simplifying it, but this is the way they found these new relations in knot theory. So in PDE, empirically, we have found that it does outperform many traditional methods. And more importantly, I'm not so concerned about this outperformance, because if you know that there is something there, eventually you can get it any way you want. But what I'm more concerned and what I like a lot better is because of the discovery. So it can really take you to regions of parameter space that somehow other methods don't consider, and it can lead to really discovering new structure and new solutions. Now, all of this is with the following caveat. Nobody knows exactly well why does it work. Okay, it works, but the numerical analysis is very difficult, and people are still, including myself, figuring out why exactly works, because then if you know how things work, then you can tune it one way or another. Okay, so this is, let's say, a depiction of an abstract explanation about why machine learning works better and can explore better regions of parameter space. If you think of your functions as some form of basis, then in machine world land, these are very nonlinear functions. And then if you plot them, there is a lot of corrugation. Once you sort of stack them together, they don't belong to nice hyperplanes in parameter space. They're all crumpled. And with that, for the same cost in, let's say, in time, you can really get closer to many points in space that before were difficult to reach unless you had a very high computational cost. So this is sort of my way of understanding why, for a fixed amount of time, for a fixed cost in terms of computational power, you can really get to regions of parameter space that before you wouldn't explore, or it would take you a lot to explore, and thus leading to easier discovery. Okay, so I'm more concerned, my work is mostly concerned about singularities in fluids. What's a singularity? Well, a singularity is whenever you have a function that depends on space and time, and then there are sudden changes and some quantity becomes infinite time. And these are examples of singularities happening in nature where the velocity, or maybe derivatives of the velocity, or here the interface between the two phases of the fluids touch each other. So I'm interested in finding singularities. I'm interested in computing singularities. And my singularities usually are self-similar. So self-similar, and again, this is not a very precise mathematical definition, but just to fix ideas, is a function that if we zoom in at a certain rate, it looks the same. Okay, and many singularities in fluids are self-similar. So I'm concerned about finding singularities of self-similar type. This is a self-similar object in real life. Maybe time to wake up. Do you have any idea what this is? Okay, well, very good. This is broccoli. So yes, so self-similar objects happen in real life. They are certainly the most stable configurations, and we see them every day. Okay, so let me skip this. This is what we found in 2022 using AI methods or machine learning. We were the first to numerically find a highly accurate self-similar solution for something called the Boussinesq equation, which you don't need to know, but what it is, but it leads to blow up for the 3D Euler equation in the presence of a boundary. Okay, so we were very happy, very surprised about this discovery, and really improved on the accuracy of the calculations of this scenario. Okay, so what's next? Now this was 2022, we're in 2024, and we have been working on this problem and related problems. And we have been able to use these techniques, understand them better, improve on the techniques, and be able to find other self-similar solutions of other equations. Now, the future, let's say, in a few years, or our dream, is to really go further and remove the boundary. So to produce a singularity for the incompressible 3D Euler equation without the presence of the boundary. The boundary is helping the singularity to form because it stabilizes. So we want to get rid of that. And this is our main driving force. But other problems and other conjectures are really susceptible to fall using these kind of techniques. And once we do that, and once we obtain a sufficiently accurate solution, we have set up a roadmap to produce a mathematical theorem out of this numerical guess, potentially obtained with AI. And this roadmap involves a computer-assisted proof. So I'm circling back to the beginning of the talk. An upshot of the roadmap is that it also allows to introduce some form of viscosity in the equations. So in other words, and this term is going to be treated perturbatively. In other words, this would mean that under some conditions that I won't write, potentially one could go from 3D Euler to 3D Navier-Stokes, which is the Clay problem. And okay, we don't know if this is going to happen. We have implemented this roadmap in the context of the compressible case, for which singularities are easier to form. I personally am optimistic. I mean, okay, I have skin in the game, but I am optimistic that the dream will become eventually true and potentially soon. And whenever that happens, computers are going to be fundamental in the journey. And just to do a little bit of self-advertising, I'm going to talk about more details, more technical parts of the whole proof in lecture 2. Just to be clear, we haven't solved the clay problem, okay? So don't come expecting a big announcement, but I will explain how to make things work. And yeah, just to conclude, this is the takeaway message. I think this interaction between computers and mathematics is extremely vibrant. There have been lots of recent progress in many dispersed fields of mathematics. Something that is interesting is that the private sector is starting to be interested and is starting to be involved. And this certainly leads to new avenues of research. So computer-assisted proofs, machine learning, their interaction with traditional mathematics. And I really hope to see many big successes in the near future using a blend of all of these techniques. So thank you all for listening. Merci beaucoup.
Many thanks, Javier, for beautiful lecture. Are there any questions or comments?
Yes.
Say that a lot of the mathematics working together with machine learning is, a lot about, like if you go to ChatGPT, if you don't give it the right query, you get nonsense. So some of the interaction between mathematics and machine learning, like you have to kind of pose the right things in the right way in order to be able to say like together.
Absolutely. Yeah. This is part of the not fully understanding how things work right now. This is just the beginning. All I'm saying is that this has a long way to go. And in the beginning, there are many gray areas, and we are like in a dark room. We don't really know what we're doing. So it will take time, but eventually, in the same way that we have gotten better at asking questions to ChatGPT, now there are prompt engineers, and everyone has his or her own tricks to sort of get what they want. We'll get better to operate with machine learning methods and be driven to whatever questions that we want to answer. I think it's a matter of time. It's just starting now. This is all I'm saying. But it has picked up very quickly, and I think it's also a good moment to sort of get into it. Not for the Businesque, fully connected and 30 by 6. I don't know if that's so in terms of size, roughly a few thousands of parameters. Not very big. This is by today's standards. This is not very big. The simulation took about half a day, which is not that much by today's standards on one single GPU.
There's something about you had one slide where you talked about what is the overall scheme for a computer-assisted proof.
Yes.
And I was and you had a pen and paper part and then a computer-assisted part.
Mm-hmm.
And I was wondering if you could comment a bit more on the computer-assisted part. Because I know there's people who computer formalized proofs where the computer is checking the logic, but it sounded like here the computer is checking calculations.
No. So I'm not talking about proof assistance or proof formalization. This is a whole different thing. Here I'm thinking of, so let's think something concrete. Suppose that I want like that this problem is, say, find a function that satisfies something, okay? Some equation. And then this analysis part is going to be recasting that equation as a fixed point, okay? So now this reduction is proving that some number, that some norm of some operator is smaller than 1. Then I can invoke some contraction mapping to claim that if I were to show that that number is smaller than 1, then I can go back in this step and prove that I have a solution. So that's what I mean. And this is very simplified, like a very simplified version of what I mean by that. But you can think of having a bunch of, or a whole lot of open conditions that the computer has to check. And whenever the computer checks them, the computer takes into account all sources of error and everything that may have gone bad throughout the calculations. Okay, but this is not really about proof verification and things like that. Yes.
Well, I think it's fine.
Okay. You mentioned that this is a good field for students.
Yeah.
So perhaps maybe can we have some suggestions on how a student might get started learning about some of this?
Maybe you should ask my own students. But okay, so why do I think it's good? It's good because the entry barrier in terms of the amount of code, the minimal amount of code that you need to get something that runs and does an okay job is very small. So then it's very easy to get hooked on it. Like you can write a code that does, I mean, not fantastically, but somewhat okay in a few hundreds of lines.
This is a testament to the tools that already exist.
Yeah. Yeah, and then it's like a game, and it's like an instant reward kind of thing. You tweak something, and then you get a number, and then you tweak something else, and you try to improve on your score, and you get hooked. And I got hooked, and it's addictive. And this is a way to sort of get students involved. Of course, doing things properly and really getting to the high scores requires more thought and a lot of time. So I'm not claiming by any means that this is easy, but there are plenty of problems. There are plenty of things that you can play with. So it's the entry barrier. I think it's quite small, and then from then you can build up anywhere. So then the sky's the limit in the sense that you can really think of like this. The murmurations, for example, they were just playing around with, like, there is some database called the LMFDB of elliptic curves, and they were playing around with them and trying to see what they could figure out using machine learning, interpolate, if you want to call it like that. And then that's how they found this phenomenon, just by playing around with those data. And who knows what the next murmurations are going to be.
I have a question. So I heard your, the origin of your work on machine learning to identify the blow up in Euler.
Yes.
That had something to do with working with geophysicists.
That's true.
Can you tell us?
Yeah. So this all, this all started with a senior thesis in the geophysics department in Princeton. All of my co-authors, we all were at Princeton at some point in space and time, and now none of us is there anymore. And we met there. So my co-authors were using these sort of methods for other PDE that don't have to do with fluids, that have to do with ice, and inferring some parameters that come from ice melting. And so in their group, one of the students wrote a senior thesis about this, and they needed a mathematician to sort of validate it in the sense that it was sensible work and that it was good. And this is how sort of we, both Tristan Buckmaster and myself, how we started to enter in contact with Yao Lai and Yongyi Wang and the student Charlie Cowen-Breen, and started working in these sort of projects. Mm-hmm. So yeah, it's really random. It's something that you could find having coffee somewhere. Really something that I would have never thought of. Let's say 4 years ago. 4 years ago, as I have said, my stance would have been like, there's no way this is going to work. But I stood corrected very quickly, and I have changed my mind ever since. And now I advocate for AI and machine learning much more. So I have changed my opinion about it very strongly.
All right, I think it's a good time to stop because there is some wine and cheese reception just there. So before that, let's thank Javier once more. Thank you very much.
Thank you.